Hello, everybody, and welcome to this training on Wikio. Today's theme is vegetation, and the study case of this training will be monitoring land cover and agricultural crops in the Alsace region. So, in this training, you will learn to use the data available on the Wikio interface to perform analysis over vegetation and agriculture monitoring. So in order to follow this training, you will have to access this Jupyter interface. In order to do so, you will have to, it's simple, just have to go to the Wikio main page right here, and this is the icon for Jupyter. So just by clicking on it, you will access the Jupyter Lab. Of course, first you have to create an account on the Wikio platform, and you should be able to log in and access this interface. And then you will be able to open a notebook. Be careful that when you open a notebook, such as the one for this training, make sure that you load the right environment to perform the Python calculations. So you'll have to click here and make sure that the Mini Wikiolab environment is selected. That way you will have all the useful libraries already at your disposal. Now we may start. So, of course, vegetation, when it comes to environmental studies, is a very crucial subject because it encompasses many fields in science and in, well, human development, such as agriculture, biology, and so on. And in today's training, we will explore the applications of remote sensing for vegetation studies and see how it can be useful, for example, for land use monitoring and agricultural monitoring. And so we'll use data that is available on the Wikio portal and which is derived from remote sensing. So first, here's a brief overview of the Python environment that we are going to work with. So in this table, you have the fundamental packages required in this training. So the NumPy uh, package is, well, very commonly used in Python for any kind of scientific computing. So you're probably already familiar with it if you've used Python before. Rasterio is especially useful for satellite images manipulation. Xarray is also a very user-friendly library to manipulate netcdf files in Python. And finally, those two packages, Matplotlib and Cartopy, are used for visualization and plotting graphs and maps. And GeoPandas is also very useful to work with geographical reference data. Um, so this is very useful for vector data, for example. With this cell, we're going to import all the necessary libraries for this training. And now we may start. So the first dataset that we're going to use is the Corin land cover dataset. It's a dataset that gives a land use cartography over all of Europe. So every pixel of the dataset is belongs to one of 44 classes, which goes from your urban area to forest, including agricultural land, etc. We'll see that in detail later. So in this table, you have a brief summary of the main characteristics of the Corin land cover dataset that we're going to use. So we have 48 land classes. So this is the ID of the product. You can click on it to be redirected to the Wikio portal and have more information on it. Oh là 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 là, j'ai fait une bêtise. So here are the datasets that we are going to use in this training. So first, we're going to use the Corin land cover dataset, which is a database classifying the land use of many of all of Europe. Putain, je recommence. Ah! So in this training, we're going to use two main datasets. The first one will be Corin land cover. So it is an inventory of the land cover composed of 48 classes. And this product is updated every 6 years. So here in this table, in this column, you have the main characteristics of the dataset with the 48 classes, the product identifier on the Wikio platform. If you click on it, you will be redirected to the Wikio portal with more information on the product and the possibility to download it from the portal also. So it has a spatial resolution of 100 meters, and this time it is updated every 6 years, and we took the dataset from 2018. So in this training, we'll be using two main datasets. The first one is the Corin land cover dataset. It is an inventory of the land use over all of Europe. So it's composed of 44 classes, going from urban areas to agricultural land, forest, and so on. We'll see that in detail afterwards. This is a product identifier on the Wikio platform. If you click on it, you will be redirected to the page on the Wikio portal, and you will be able to gather more information on the product and download it. It has a spatial resolution on 100 meters, and as it is updated every 6 years, today we took the latest iteration of the product, which is the dataset from 2018. So, of course, we will study vegetation over several different years, close to 2018. So we'll assume that the land use hasn't changed that much around this period. The second dataset that we're going to use is the vegetation phenology and productivity dataset from the Copernicus land monitoring service. So it also has a resolution of 100 meters, and it has a Rigeoli resolution. And we will took data from 2017 to 2022. So you will see that it provides many different vegetation indices, especially when it comes to phenology, which is what we're going to look at in this training. So you will see in the next sections what we will do with it. And same thing, if you want to have more information on the product, you can either go to the Wikio web portal to find out more and to download it, or you can visit the dedicated Copernicus pages to access the more detailed documentation. So this link is for the Corin land cover dataset, and this link is for the phenology dataset. So here is a quick section about how to retrieve the dataset. So of course, you probably already know that you can retrieve it directly from the Wikio web portal, from this interface. So here is another method to retrieve the data directly from Python. So first of all, you will have to execute this cell to enter your credentials, and if you haven't already done it. So this will create a point HDRC HDRC file in your root directory, which will, with your credentials saved on it, and this will allow you to access the Wikio API and directly download data from Python. So now that you have done this, you can send requests to the Wikio API. For example, in this folder is a request for the Corin land cover dataset. So this is this file written, so it's a JSON file. And for example, here, this is what it looks like. So it's for this dataset, the request is quite short. Normally, you would also have to, for example, enter the date range you want to get, the spatial area of interest that you want to have your data on. But with the Corin land cover dataset, you don't have such options. So here you can see that I've selected the 2018 dataset. And of course, this requires some formalism, and so the request has to be in a very specific format. And if you want to simply copy paste the request, you can build your requests from the portal. For example, so this is not the Corin land cover dataset, but you will see where I'm coming from. And then when you launch the request, you can go to the job tab, and click on this icon, you will be able to display your request. So here it's a very long request because it's a different dataset, but it's the same way of functioning for the Corin land cover dataset. So you can either show the API request or go to the job and click on this icon. So now that you've saved the requests in the text file with the JSON format, you are ready to download the data. So here's now a quick overview on how to retrieve data from Wikio. So you've already been shown how to download data from the main Wikio interface here. But here I'm going to show you how to download data directly from Python. So first of all, you need to create a .hrc file. In this file, your Wikio credential will be stored, and this will allow you to download data from the Wikio API from Python. So if it's not already done, you can execute this cell, which will ask you to enter credentials. So when I execute it, it doesn't do anything because my file is already built. So once that's done, you have to write a data request. So in order to build one, it's quite simple. So what I suggest is to go to the main interface and start clicking on the product downloading icon. So from that, once you've specified all the different parameters that you want, at the bottom of the window, you will have the Show API Request option. And this will allow you to copy-paste the requests from the interface to the JupyterLab interface. So here, for example, is the Corin land cover request, data request. So you can see that here I've selected the 2018 dataset. So, and then you'll have to save it in the JSON format. So here, the data request is located in this folder. So in the training vegetation, data, Corin, and Corin request.json. And now with the JSON Python library, you can load it to visualize the request in the notebook. So this is it, and it's stored in the data variable. And now you are ready to download the Corin land cover dataset with this cell. So of course, depending on the product, downloading data from Wikio might take some time. So here, to avoid this, we've already pre-downloaded the product, so you don't need today to download to execute this cell. But now you know the method to download data from the Wikio API. Now, in this section, we are going to take a first look at the Corin land cover dataset. So, first of all, we've pre-cropped the dataset over the region of Alsace in France, because when you download the dataset, it downloads your data from all over Europe, so it's way too big. We've reduced the dataset to study one region in particular. So first of all, the dataset is provided with this file, text file, which gives the lists of the different classes that are found in the dataset. So we have here, as you can see, our 44 classes. So the first class is a continuous urban fabric. You have green urban areas, and all those categories are about agricultural land. And at the end, we go to more natural landscapes and water. So what's important here is that we have a Copernicus indicator, which is more explicitly explained in the user guide of the land cover dataset. So we can see that categories starting with 1 here refer to urban areas. Categories starting with 2 refer to agricultural land. Starting with 3, we have natural landscapes. With 4, we have so other natural landscapes. Wow, c'était quoi là? So categories starting with 1 refer to urban landscapes. Categories starting with 2 refer to agricultural land. With 3, it's more natural landscapes such as forests. With the category starting with 4 concerned wetlands. And finally, starting with 5, we have water areas. So we're going to open the land cover dataset with Rasterio. And as there are more than 40 different classes, we are going to simplify the dataset and gather all the 40 classes depending on their main category. So we're going to gather all the urban areas together, all the agricultural areas together, and all the natural areas together. So as you can see here, we have only 5 categories left. And with this cell, we're going to visualize the Corin land cover dataset over Alsace. So on a quick note, to figure out the colors for each area, we've simply performed the average of each color canal. So here are the values for the red channel, green channel, and blue channel. And we perform the mean for each of them to have a global color for each category. So as you can see here, so in red, we have all the cities of Alsace. So for example, here we can clearly distinguish the city of Strasbourg, for example, and other neighboring cities. In yellow, we have all the agricultural land of the region, and here in green are the more natural landscapes. So probably here it's probably forests. Now we're going to focus on the agricultural profile of Alsace. So we're going only to look at the yellow area here. So we have seen that the agricultural category has several subcategories. And now we're going to try to see how those categories are distributed in Alsace in order to have an overview of how the agriculture in the region is organized. So here are the agricultural subcategories that can be found in the region. So we can already see that most of it is non-irrigated arable land. So of course, the current land cover doesn't provide with every possible crops that can be cultivated. We have a vineyard. We have vineyards. We have fruit plantations, pastures, and other cultivation patterns. And so we're simply going to draw a pie chart to find out the different proportions of the agricultural fabric in Alsace. So we can see that the vast majority, about 2/3, consists in non-irrigated arable land. We have about 4.5% vineyards and 2% fruit plantations. We have 12% pastures and about 15% of other types of cultivation patterns. So this is analysis that you can reproduce on any region that is covered by the land, by the current land cover. So I highly recommend you to explore the dataset and do this on other regions. So now we're going to study the vegetation phenology over the Alsace region using the Copernicus phenology dataset. So as a reminder, you can access the Copernicus page for the product to know more about the different variables that you can find in this product. So, sorry, I'm just going back to section number 5. Here we are. So in the first subsection, we're going to study the lengths of the seasons for each year between 2017 and 2022. So in the vegetation phenology dataset, a season is the length where the... Oh là là, je m'en sors pas. So in this dataset, the vegetation phenology parameter is the leaf area index, so the fraction of pixel covered by leaves. And so in this first section, we're going to study the length of a season. So the leaf area index follows a seasonal pattern, and we're going to call season the period where this index is high. So, for example, on this figure, the length of the season will be referred to by the C variable. So the season length data has been saved, pre-downloaded also, here in this folder. So we downloaded one for each year. And so here is the request for the data that you can also call from the Wikio API. So now that we have this data, let's just have a quick look at one of these TIFF images. So this will be done with this season. So here with this cell, we just open the different files, and with this one, we'll just plot the graph. So here over Alsace and any pixel with vegetation information, the length of the season for each pixel is plotted in days. So as we can see, if we remember, those areas which are mainly blue were the agricultural areas, and they are quite short compared to the forest areas, which have much longer seasons, which is consistent because well, forests have oh la la, which makes sense because in forest the trees are permanently there, and in agricultural land, depending on the crop type and how it is cultivated, the period of time during the year where leaves are visible on the ground may be a lot shorter. So now we're going to correlate the land use covers types from the Korean land cover dataset with this season length dataset and see how the season lengths differentiate according to the land use category. Hop là. So you can see that for each category that we've seen previously in the agricultural type of land, here we have computed all of the values of season lengths belonging to each of these categories. So as we can see, non-irrigated arable land tends to have a lot shorter seasons than vineyards, for example, whereas the other categories, especially complex cultivation patterns, fruit tree and pastures, seems to have a more homogeneous more homogeneous season length values distributions. And so this analysis was done only for the year 2022. What we want to see now is what is the variation over each year of the season lengths for each category. Because of course, each year gives different climatic conditions. 2022 was exceptionally hot, for example. So we'll see how the season lengths vary from year to year with the next figure. Okay, so now we have computed the average season length for each year. So basically the orange bar here. We've computed it for each year for each land use category. So what can we see? We can see that for most culture types, 2022 was characterized by shorter seasons, except for vineyards here. And on the contrary, 2021 was characterized by longer seasons for most of the agricultural crop types. So this is quite interesting. And in the last section, we're going to focus on one of the types. Here we'll take fruit trees and berry plantations and see what climate conditions might have influenced those years to have such different values. So to have a more in-depth analysis of the seasons for fruit trees and berry plantations, we're going to use two additional datasets, also from the vegetation phenology dataset from Copernicus. This time we look at the start of season date variable and the end of season date variable. So just to remind you what those variables represent, if we go back to the figure here from the Copernicus Vegetation Phenology user guide. So if you remember, the season refers to the C variable, and the start of season will be the date corresponding to the A here, and the end of season will be the date corresponding to B here. So analyzing these two dates separately will allow us to have a more precise analysis of the seasons over the region. So here with this cell, we are going to open the datasets. So just like before, we have the start of season folder here and the end of season directory here. So we have downloaded the data for the 3 last years, 2022, 21, and 20. And here is an example of the requests to send to the Wikio API. Okay, so here are a few functions. I won't go into too much detail here, but I will quickly show you the user guide of the dataset to show you what those functions are about. So as I suggest, you go to the vegetation page on the Copernicus Land Monitoring Service website that I have already shown you, and select the documentation for the vegetation phenology and productivity parameters. So select, for example, end of season date. And here you should have access in the technical documents to the product user manual. And here, this will give you, on this page number 22 here, you will have an explanation on the date format for the start of season and end of season variables. So as you can see, it is stated in the user guide that the format of the dates in this dataset are as follows. So the first two figures refer to the year, and the last three figures refer to the day of year. So for example here, this date will be the day number 30 in 2018. So of course, this format is quite easy to understand. However, this is not something that is supported by Python. So which is why we have provided this function here, which converts the Copernicus format to a classical date format for Python, which will allow us to manipulate the data a lot easier. And also, this function has been written to harmonize the date value between years, because the datasets from 2001, 2021, and 2022, on those datasets, the dates have been been calculated differently from the previous years. So I built this function to correct these two datasets and to harmonize the dates with the previous years. So this is what's done in this cell. This is the harmonization. And this is the conversion from the Copernicus format to the classical datetime format for Python. There is a lot of data to process, so this should take a few seconds. Okay, it's finished. And now we're going to plot the dataset histograms to see what the data looks like. So here we're plotting the start of season dates, and here the end of season dates. And this is what we have. So each color refers to a year. And what we see here is quite consistent. So in light blue, here we have the start of season dates for the 2020 season. So we can see that it starts in January, slowly in January here, and peaks around the springtime. And finally, the end of season starts during the middle of the summer and ends by fall. And the same goes for 2021 and 2022. So this has been processed for all the Alsace region. We're going to only select the pixels in this dataset that refer to fruit trees and berry plantations. So if we refer to the text file that we have open here, we can remember that fruit trees and berry plantation have this number here. And if we remember that it starts with 0, we have to refer to fruit trees and berry plantation by using number 16 here. So let's do this. And now we're going to plot the start and the end of season for each year, um, only for the fruit trees and berry plantations, because now we've only selected the pixels referring to this type of area. So as we can see here, it is also quite obvious that in 2021 the season was much longer than in 2022 and in 2020. And finally, in the final section, we are going to use temperature and precipitation data to try to identify what possible factors could explain this longer season in 2021 and this much shorter season in the other years. So as we know, temperature and precipitation are two key drivers of vegetation growth. So the dataset that we're going to use is climate data. So it is also available from the Wikio portal. So this is the dataset that you can also open in the interface. We also have pre-downloaded the data, which is here, climate data. And so we have downloaded two variables, so the temperature here, which is the surface temperature at a 2-meter height, and the total precipitation, TP. So this is monthly data, so this resolution is useful because we're trying to find out seasonal patterns. And to open this data, it is a netcdf file. Well, should I say a series of netcdf files, GRIF files here, which is an equivalent format. So, and to open them, we're going to open them with the library xarray. So this will take a few time. As you can see here, there are many datasets. There is actually one dataset for each month, and we're studying 3 years, so we should have 36 datasets. Yes. And we've opened them all using a loop here. This is the temperature dataset. And then we concatenate all of them in a single variable with xarray. So here is the full dataset. So as we can see here, it is characterized by several coordinates, the key ones being time. So we have one time value per month during the 3 years, latitude and longitudes, and of course the temperature variable here. So you can click on these icons to have more information about the variable. Here, 2-meter temperature, the units, quite important also. And here you can have a brief overview of the actual values in the dataset. So what we can see here that is important is that the dates here are not necessarily in order. We can see that it starts with August 2021, ends with March 2022. So we're going to sort the dates so they are in order. We can also see that latitudes go from 19 to minus 90 degrees. We also want to sort this so they are in order. And finally, here the longitudes go from 0 to 360. And in Python, it is easier to work with data with longitudes going from minus 180 to 180 degrees. So with this cell, we're going to shift the longitudes and sort the coordinates. And now, so the latitudes are in order, the dates are in order, and the longitudes have the proper values. Okay, so now the next thing we want to do with the data is to subset it. So to do so, we'll use the slice function in order to select an interval of longitudes and an interval of latitude to select our area of interest, which is the Alsace region. So now that we have executed this cell, we can take another look at the dataset. So here we can see that we have a much smaller latitude and longitude range because it is centered now around the Alsace region, and we still have the 3 years of dates. So one thing you can do with a dataset, an X-array dataset, is that we can plot it on a map. So using Cartopy and Matplotlib, we can draw this on a figure, like here. So here, for example, I'm selecting the date 2021, 1st of January, and I'm plotting the temperature over this area. So of course, we focus on a small region, so we only see a lot of pixels. So for example, here is the temperature anomaly in January 2021 here. So we're talking about anomalies because here the temperature are computed with a reference period, which is the average temperature over the 30-year period, 1981 to 2010. So this is something that we have requested in the request for the climate data here. Let me just show you in the editor. So here we have selected here the surface air temperature, product type anomaly, and the climate reference period is 1981, between 1981 and 2010. So this is why we have temperature variations instead of absolute temperature. So knowing this, now we have plotted this on a map. Now what we want to look at is a time series of temperature and later on precipitation. We're going to perform exactly the same steps with the precipitation data and compare this time series to the vegetation phenology that we have studied before. So with this cell, we're going to perform the spatial average of the temperature. And now we're going to perform all the same steps with the precipitation data. So opening the files, sorting the data, subsetting it around the Alsace region, and performing the spatial average. So this will take a few seconds. Okay, this is done. And now the last thing that we're going to do is to plot side by side the season's length with the series of precipitation and temperature. So it's a very big cell, only dedicated to building the graph that we're going to look at now. So I've executed it, and this is what we can see here. So in blue, we can see the precipitation anomalies, also with regards to the 1981-2010, the reference period. In orange, the bars represent the temperature anomalies that we have already studied. And here, in the different shades of green, there are the seasons as computed from the Copernicus dataset. So we can still see that the 2021 season is significantly longer than the two other. And if we look at the temperature and precipitation data, we can see, for example, that here, especially at the beginning of in the first half of the 2021 season, we had quite a lot of precipitations with, well, reasonably average temperature overall during the season. And on the contrary, for example, here in 2022, the spring and summertime were exceptionally hot in this region. So we can see this with the very high orange bars. And on the contrary, it was quite a dry period here with very high deficits of precipitations in May here and in July here. And here in 2020, we have a similar pattern of precipitation deficit from April to July with, well, quite cooler temperature overall, but an exceptionally hot April and hotter. But here, the deficit of precipitation is probably a bigger driver of the season's length here than temperature. So this shows that the early season, which was very humid in 2021, and the precipitation deficits were the key drivers of the differences between the season length here. Of course, there are many other factors that we haven't been able to look at, but this is probably a good lead. So we are reaching the end of this training. So to summarize, we have looked at the land use in the Alsace region with the current land cover dataset. We have computed a few vegetation technology indices and correlated them with precipitation and temperature data. So section 8 gives you a few exercises. Some of them are already mentioned, like trying to perform the analysis on other areas that are also covered by the current land cover datasets and the vegetation phenology datasets. So if you have another region you're interested in, feel free to perform the similar analysis on it. And this is the end of the training. We hope you have enjoyed it and that you have learned plenty of new methods to manipulate vegetation data with Python. And if you have any questions, don't hesitate to contact the supports with this email. So thank you very much for your attention and well, hopefully see you next time.